for linear algebra, and as you have seen that I'm not doing just as it should be taught in classroom, right? Linear algebra, and it can take more than two courses, even in fact, two semester courses to get the flavor of linear algebra. But we are taking only two classes, so it's a comprehensive review, and I'm just covering those portions which are otherwise it is difficult to understand quantum computing, so especially for the beginners, right? So I today also I'll be following the syllabus also. So it's a matrix computation part. So I'll touch some of those portions and give an overview of the certain things, especially matrix factorizations, matrix inversion process, both in classical context and little bit on the quantum context. So although the quantum context was not there in the syllabus, but I thought to cover a bit so that you get some motivation while you are studying this topic, right? So without doing much introduction, let's start. So please allow me a minute, maybe, um, just to get the setup and everything done. So I need to keep open the chat also to listen to your questions and all. So, mm. and yeah. So hope you can see my board, right? So can anyone confirm that this is visible, the blackboard, just in the chat box? And yesterday I shared the notes to Professor Santosh sir, so he'll be sharing the notes in time. And so today, so everybody, almost you have heard that people says quantum computing is fast. Now, fast is with respect to what? Is it always fast for all problems? The answer is no. It is fast for certain problems. And when I say it is fast in terms of time, memory, right? Or in terms of what is the criteria to say fast, right? So whether it's theoretical, it's practical, these are other norms also. There are various notions. So one of the thing is to check the complexity, right? So it's important to check the complexity. Now, complexity, I won't go for details of big O notation, theta notation, and all. But what I will be interested is that if you design an algorithm, so typically in quantum computing yesterday, what we have seen that if we describe our problem, right? If we describe our problem and represent into quantum states, right? So there are only two things. One is quantum states, that means quantum state vectors, right? So they are typically vectors, states are vectors, and quantum operations. So operations that you need to do, they are basically matrices, right? Now, in higher dimension, they can be other mathematical object, but in general, for now, quantum computing, so you describe your problem as a state encoding or a vector, and whatever operation you do, they are typically matrices. In fact, if you consider an isolated quantum system that follows the Schrodinger equation, I h bar del t psi t, right? Psi x comma t, for example, right? Equals to h psi x t, right? This is your this time evolution equations, right? So now, if you solve this equation to understand the evolution of the quantum state, now instead of simply function, you can put it inside a vector like this notation, and eventually this H becomes a matrix, right? So matrix, and if it is a n cross one dimension, it becomes a n cross n Hermitian matrix. Typically, any matrix, it should be ordinary square matrix, but to get the eigenvalues of these observable to be real numbers, right? So if you want to get the lambda of H to be a real number, right, then H has to be Hermitian, H star equals to H, right? This is the criteria. So this is this is called a Hermitian matrix, right? So now if you solve this equation, this is a ordinary differential equation with respect to time, right? If you solve this equation, so your evolved state, I can write it as psi t plus say delta t, for example, right? Or simply I can write in terms of the initial time, right? So at psi x comma t, I should write um, x comma t equals to e to the power IHT just by solving this ODE equation with respect to time. Take the time and the space as the independent variables and solve it. Then you'll be getting e to the power minus HT psi x comma 0 t equals to time 0, right? So this is the solution of my one-dimensional the ODE equation for the time evolution of wave function psi t, right? And the wave functions are denoted by the state vector, right? So then this thing we have seen, this is a unitary operator, right? Unitary matrix, basically. Unitary matrix. E to the power IHT. Now there is a whole theory how to prepare these things. So I'll come back maybe in a later course, QT-05 or something like that, and I will take an entire class on this e to the power IHT part. But for now, it's just a unitary matrix. Okay. Now, so typically, you have encoded a circuit in a qubit set, for example, Q0, Q1, and Q2. Yesterday, you have designed the circuit for the correlation finding, right? Or the distance L2 distance call computation using the swap test circuit. So something like this, right? We have seen this example, right? And this is entirely is a unitary matrix, right? This is acting as a whole unitary matrix because this is a 2 cross 2 unitary Hadamard matrix, 2 cross 2 unitary Hadamard matrix. There is nothing means identity matrix, nothing means identity matrix. So it's all together. You can see the dimension of the this part, and this part, right? And this is a C swap gate, 8 cross 8 matrix, right? So it's a product of three matrices of 8 cross 8 dimensions. So altogether, it's a 8 cross 8 unitary matrix, okay? And you have three initial states, right? And each of these qubit can be represented in the gate 0 and gate 1. So they have 2 cross 1. So altogether, it's a each 8 cross 1 state vector. At the output, you'll be getting a 8 cross 1 updated state, right? So this is the whole picture. It's just simply a matrix times a vector multiplication. Matrix times a vector multiplication, right? Of course, if you consider noise and if you go the density matrix approach, we'll be seeing next week, right? Okay, correct. So somebody, Dr. Venkat sir, so told that it's a to the power IHT by little h. So I have taken little h equals to 1. Okay, Planck constant for simplicity. It's a constant, so there is nothing to compute on the constant. It's just a constant, right? So you can take h bar equals to 1. Just I removed the time notion, right? So now we need to understand that if I design an algorithm, and of course I design by algorithm, I mean whether I design something which can efficiently prepare the state or efficiently prepare this U, right? Either of this, right? And then whatever I get, say for example, I get the product U and Ket psi, that is equals to Ket phi, and I can do some good algorithm for post processing, right? Post processing also before the measurement or after the measurement. If I do measurement here, I get certain probability, right? Certain probability amplitudes. So these are various computational basis versus the probability, right? Of the computational basis states versus the probability. These are say Ket K at the computational basis, and these are the probability of the Ket K, getting the Ket K, right? So basically you can do after classical measurement. After measurement you can do classical post processing. Before measurement you can do quantum post processing. So you have various scopes to improvise certain things, but whenever you introduce certain quantum algorithm, so you need to compute the complexity part, right? So let's go back to the classical picture and understand what complexity means. So I am assuming that there are some participants who might not have good or forget the complexity notions, right? So let's talk about complexity. So let's start with vector dot product. Okay. Vector dot product. So suppose we have two vectors, x and y, right? And they belongs to the vector field Fn. So I can take a general field as F, right? It's a general scalar field. Scalar field. If I take the R part, this is real scalar field, right? Real numbers, set of real numbers, and this is the set of complex numbers, and so on. If I take Fn cross one, as it can be Cn cross one, that means complex vectors. So a set of complex vectors, as well as I can take R. I can take real set of real vectors, right? R n cross 1, right? So it's a set of real vectors, right? So set of real vectors are n cross 1, set of complex vectors are Cn cross 1. So I can represent them as a general notation Fn cross 1. Similarly, numbers can be scalar real numbers, scalar complex numbers. So I can in general represent as F, right? So when I do operations, for example, I write X transpose, right? So X transpose Y is basically, so considering that that time I take the real case, right? Otherwise, if it is a complex case, so I could write x star y. For if it is x and y, they belongs to C, n cross 1, right? So n is the number of elements. So little n or capital N, whatever. If you are okay, you can write that. So so generally, we denote by X transpose. Say X is a vector 1, 2, 3, right? If that is the case, so typically it can be row vector or column vector. If nothing is told, it's a column vector. Otherwise, you can take X like this, and then X transpose will be this 1, 2, 3, right? So this way. So this is just a notation, right? And basically X transpose Y is also known as the dot product. Okay, there is one more notation. Sometimes we write as X dagger Y. So dagger often we represent as a general notation, right? General notation both for star and transpose. Okay, so these are just some notations, although these are I mean, not standard. People use it in various way, but in IEEE format, typically we prefer this kind of notations. Dagger, this is called a dagger notation, asterisk notation, transpose notations, right? And this is the real set of real numbers, complex numbers, and the general scalar field. Okay. So the definition is that X transpose Y, that's equals to sum of xi and yi. What I want to do, I have two vectors and I want to do the dot product of the vectors. So basically, say I equals to, sorry, I equals to 1 to little n, right? N number of elements is there in the x vector, and n number of element is there in the y vector, right? So for example, if I have 1, 2, 3, and I am doing dot product between, say, 2, 3, and 4, right? So individually I do multiply. So 2 into 1 is 2, plus 2 into 3 is 6, plus 3 into 4 is 12, right? So what is the answer? 8 plus 12, 20, right? So this is the thing that is done on a dot product, right? Now, what is the complexity of doing this, right? So, so what I have to do? I have to calculate this. Suppose A equals to X transpose Y, right? This is something expected output, right? Output. And what are the inputs? Inputs are X bar and Y bar. These two vectors are the inputs, right? So let's try a pseudocode for this. So let's initialize this variable A equals to 0. Okay. And then how many numbers are there? There are n numbers, right? So n times. So if you look at this summation, I equals to 1 to n, right? So for this summation, or sometimes when you see this product, right, I equals to 1 to n. So both for this and this, you can use the for loop. For I equals to 1 to n, we have to do this. We have to update this scalar as a plus initial value plus xi times yi, right? And then end the loop, end for loop, and return a. That's the pseudocode for this dot product. So this is the algorithm for doing the dot product, right? Okay. So this is my input, right? Um, someone is asking X and Y should be perpendicular, right? No, not necessarily they has to be perpendicular. If and only if X and Y are orthonormal vectors or orthogonal vectors, then fine. Otherwise, they can be typically any two vectors. Just to dot product, they can be any two vectors. Okay. And when we'll do quantum computation, you have a quantum state Kate psi and you have a quantum state Kate phi, and they may be perpendicular, they may not be perpendicular. That is not the case. But suppose you want to do the dot product between these two vectors, right? So dot product between psi and phi. So these are the additional condition that they are normalized, means their norm equals to 1. For these two vectors, norm equals to 1, right? And also this Kate psi belongs to complex n cross 1. Okay. And so phi. So these are additional constraint, but in general, this is true for any this dot product is true for any vectors, irrespective whether they are quantum state or not. Okay. Now, what I did is basically every time you are multiplying this x and y, right? So xi and yi. And basically this is the computation for that. You initialized with some zero value, and every time you are multiplying, take I equals to say 1. So first element of x and first element of y, they are doing dot product and adding it to the initial value. Similarly, you iterate second time. So your x2 value, that means you see the example, the second value is multiplied with the second value of the second vector, right? And added to the initial value. So first initial value was 0. Next it was 1 into 2 is 2, and 2 into 3 is 6. So 6 is added to the 2, and so on. So this is the philosophy of doing the dot product, vector dot product, right? Now what we have done so far is two things. One is the how many multiplication I have done. So I have to calculate the arithmetic flops or computations, right? So multiplication. So you can see how many multiplication I have done. In scalar multiplication I have done, right? Because individually xi and y are the scalar numbers, right? So in scalar multiplication. And then how many additions I have done? So I have done n minus 1 scalar addition, right? scalar additions. So that means total number of operation, if I take the polynomial order, right? So total operations will be total operations, how many? So it's if you add the total operation, multiplication and addition, n plus n minus 1, that's the 2n minus 1, and that is equals to order of n, right? So that's the complexity, right? That's the total operation complexity for this dot product. Just simply dot product, right? And you may now ask me why it is so important, why vector dot product is so important, right? This is a very, very, very simple algorithm or very, very simple method, but why it is so important? Um, so so let's give an example. Suppose you are classifying two objects, ferromagnetic or antiferromagnetic object, right? Or cat versus dog, or it can be your apple versus orange, or it can be to a person who is belonging to nation one or nation two, or it's you are getting some basically signals from the space, and you need to say whether it's a enemy target or the friendly target, or you are getting some signals from there are thousands of examples for classifications, right? And typically, suppose you get some signals, and it looks like this. Suppose this is your first feature vector, right? From object one, and from object two, suppose this is your second um, second um, second basically class, right? And then maybe something like this, right? So often it is difficult to classify them with a linear decision boundary, right? And we design a kernel, and we convert this problem from domain one, say this is the feature set x1 and x2 is the first feature set, and in the converted domain, suppose this is your y1 and y2, right? So we do a kernel basically transformations, right? So it's a time domain to frequency domain, it's some domain A to domain B, or any two domain, right? Between two domains, say suppose this is your domain A and this is your domain B, right? Such that you get your one feature here and another feature here, right? Sorry, I'm drawing the opposite thing, right? um so you get one feature here, say, and you get another feature here, and now you are able to draw this decision line, right, or the hyperplane, right? So how do you do that, right? So you typically create two feature vectors, say phi1 and phi2, right, corresponding to different class, and you calculate the dot product between them, right? And that's what you call a kernel, right? And after applying the kernel, you convert from A domain to B domain, right? And then you design this hyperplane, and you say, okay, if it is above the hyperplane, it is class A, and it is below the hyperplane, it's class B. And this is specifically called the kernel SVM algorithm, right? But it's very nice algorithm, right? This dot product is a very simple thing, but it is used in a very complicated situation, you can now realize, right? So that's why it is so important, right? And yesterday we have seen how to compute these things using the Swift circuit, right? And later in the quantum machine learning literature, so you will see that how it is actually happens, and all with details of the literature course and everything, right? So by most likely by Dr. Anupama, she will be teaching this part. But in general, the context, this order of n, this context is important, right? So now assume that the signals or the images or the features has very large dimensions, right? Say for example, you have unknown data set, right? Or you have a class, just not binary. It can be m-ary class, or very large number of classes are there, right? Say whether it's a particularly type A, type B, type C, type D, type of cancer, breast cancer, or some other cancer type, and you need to detect this particularly classification, which particular disease the particular person has. So these are very critical problems, right? We daily face a lot. Now, how many features you want to take, and you need to basically compute on all those features, right, for various purposes. And that's why this order of n complexity, if n is the This is just for the dot product complexity, right? But there are additional steps in the SVM algorithm, so that part I haven't considered. This is just for the dot product part. Now, if n is very high, right, then linear complexity itself is not that great, right? So although fine, linear is fine, but I mean, let us see. This is not just the dot product thing. Let us go a little beyond these things, right? So because then only you will understand more how this is so important. So second part is the outer product, vector outer product, right? So basically, to do the outer product, so our input will be x bar and y bar. These are the two vectors, right? And we need to calculate some a that is equals to x bar y bar transpose, right? So it will be a matrix. Say for example, if something is 1 cross 2, 2 cross 1 is one vector, and another is basically 1 cross 2, right? So if you do this kind of multiplication, right? So 2 cross 1 and 1 cross 2, it will be 2 cross 2 matrix, because first one is basically a column vector and the second one is basically a row vector, right? So 2 cross 1 means 2 row 1 column, so it looks like this, right? 2 rows and 1 columns. And the second one is looks like this, right? So 1 row and 2 columns. So if you multiply these things, so basically you'll be getting 2 cross 2 matrix, right? So better to take an example uh, so that it is easy to understand, right? So 2 cross 1, right? So basically say 1, 2, and this is 3, 4, right? So it's a 2 cross 1 and this is a 1 cross 2, right? So then if you multiply these things, right? So this is outer product, right? And you will get 2 cross 2 matrix, right? So then what's the complexity of this, right? So if you have now we similarly we can do, suppose these two vectors, m vectors has dimensionality. Say I'm taking only real numbers, for example. Let's remove the complex part, and it is suppose or take generic. Okay. So let's take f m number of elements in X for the vectors of m dimension, and Y has element of n, right? So ultimately, if you do the product, right, so we should get mn cross a matrix of f m cross n, and then if you want to do that, so basically so what we have to do is we have to iterate. So how many elements are in this matrix? So for there are two matrices, right? So one is this one, this particular vector. Another one is this one, right? So for every element here in this particular vectors x bar, right? And this particular vector, say y bar, there are two elements, say this and this, right? These are not zero, suppose, right? So you have to multiply this with this, right? This with this, and you have to continue this way, this with this, and this with this. So in this way, you have to multiply this with this, and this with this, again this with this, and this with this. So then, so this is a 3 cross 1, right? And this is a 1 cross 2, right? So you'll be getting 3 cross 2 matrix, and each time you multiply, so you'll be getting, there are 3 rows, so 1, 2, 3 rows and 2 columns, right? So you can fill this matrix, right? So basically then how many times I have to so there are two for loops, right? So one for loop is, if I write the algorithm like this, um, so input of the algorithm is x bar and y bar, right? And so x bar x bar belongs to the fm, and y bar belongs to fn, right? And then our expected output is a, which should be a matrix of f m cross n, right? So now there are two loops. One is I have to iterate over this vector. I have to iterate over this vector, two iterations, right? So for I equals to 1 to m, do, and then again I have to do for j equals to 1 to n, I have to do 1 to n. I have to do aij is a variable. You can initialize this variable aij equals to 0, and you can so basically it's not needed in fact in most of the current setup. So you can just directly do this computation. So each time you can write this way: x I dot product with y j. This is I and this is j, right? Every time, then you need to close the loop for this one, and you need to close the loop for this one, and for, right? So then I can return the matrix A, right? So then in this way you can see we have done basically two particular iterations. And then how many operations I have done? I have done m times n scalar multiplications, right? So my total operations will be order of mn, right? You can also initialize with a variable 0 and continue. So the addition part will be absorbed by m times n, right? So this is the complexity you can see. Now if m equals to n, then you can see it's the order of n square complexity, right? This is my complexity, operation complexity, right? How many operations I do. This is important because nothing runs on the air, right? So f is a field, right? It can be scalar field, it can be vector field, it can be vector field with real number set, or the complex number set. So initially I just discussed here. I discussed in detail what I have considered f, right? Yeah. So so any operation we do on a laptop, on a calculator, on a mobile phone, or on a quantum computer, so every operations, even you simply add 2 plus 2 equals to 4, for each such operations, right? It takes the hardware. There is something, right? So because Shannon said information is physical, right? And next week we'll detail this part. Information is physical. So in your laptop, in your mobile, there are transistors, right? They are doing these operations, these additions, multiplications operations, right? And in a logical level, they are the CMOS or the TTL logics, right? On a quantum computer, it's superconducting chips. You are using the microwave pulses, or you are basically using some sort of in NMR technology, you are controlling the magnetic field and all. So you are investing money, you are investing energy, right? And you are investing lots of the control equipment to do this operation. So that's why this is not just math. This is every n square, there is somebody who is working for this, right? Somebody is working to do this, right? So similarly, this is important, and I am not detailing each and everything, but just to give you a summary, another part is the matrix vector multiplication, right? Matrix vector multiplication. So next time when you design algorithm, please keep this point in mind, that what is the complexity of your algorithm. Of course, you are proposing a solution. How good is the solution in terms of memory, in terms of time, etc. Okay. So so typically, if you do a matrix vector multiplications, right, and suppose your A is f m cross n, right, and your suppose x is x vector is f n, right, and you want to calculate y equals to x. This is the most common equation on earth. Okay, for all industry. If it is a civil engineering also, this is the equation for their stress strain or CFD, computational fluid dynamics. Everywhere this equation is common, right? So in operation, research, finance, so these are just your various market variable, product price and the outcome, right? How you set the price and all. So this is a linear equation, is very common, right? So y equals to x, and we'll detail this part today, just in the second half of the lecture, right? So and we'll find the complexity to solve this, right, with the matrix inversion process. So just to get this y, so you can see yi, because y is a vector, A is a matrix, so it's a m cross n matrix, it's a n cross 1 matrix, so the product y is m cross 1 matrix vector, right? X is a vector of n cross 1 and A is a m cross n matrix. So there is m element, right? So basically it's a summation over j equals to 1 to n, right? And aij xj, right? For I equals to your um, I equals to 1 to m, 1 to m. So you can put another loop here to vary the I, right? I did not put. Basically, there you for this I part, you can put another summation block here, right? For I equals to 1 to m. So precisely you can write this way, right? So this is not needed. So you can write compactly in this way. So now what is important is that if you do this thing, what is the complexity of this part? So basically the complexity is order of mn, and if m equals to n, so the complexity is order of n square, right? This is the complexity of matrix vector multiplications, right? So now the another part is matrix multiplication, matrix multiplication. So suppose A is your f m cross p, and B is another matrix, it belongs to p cross n, right? Then AB, that is basically, suppose it is denoted by C, right? So that's f m cross n, right, is a matrix. And to calculate this part, you will find that the complexity is order of mnp, and if m equals to n equals to p, this complexity goes to order of n to the power 3, right? And this is why more computation you want to do, right? So you are getting more and more memory requirement or the time requirement, right? So it's this many operations you need to do, right? So and so on, we'll see in the inversions part. But something that is important is that can you reduce this complexity? So there are some variations of the algorithm. So this is by general way. There are other advanced way to do this. So I'll today I won't go details, but I'm giving you the name so that you can later study this part. So Strassen algorithm. So there is one algorithm to solve the matrix multiplication in a better way, right? In a block encoding way, and the complexity is order of n to the power 2.807, right? Slightly better, but for large n, for large dimension, large n, right? And then there is another method called the Coppersmith Winograd method, which solves the matrix multiplication with order of n to the power 2.376, right? So this is basically used for very asymptotic analysis, very large and asymptotic theoretical, right? So these are various methods for matrix multiplications, right? And I'll go for the inversions method in the second tab, but before that, let's again go back to the quantum computing part, right? So so initially you are creating a quantum state for you, right? Suppose suppose you have a molecule, right? Say NH4, right? Ammonia, right? And you know all the electronic configurations for nitrogen and the electronic configurations for hydrogen. So you have a molecular so this is basically N is an atom, right? Hydrogen is another atom. There are four hydrogen atom and one nitrogen atom, right? And you have a molecular Hamiltonian, right? Molecular Hamiltonian that describes the ammonia, right? Right. So for this problem, right, basically, what is the wave functions representations for the molecule NH4? Suppose that it's psi, ket psi, and suppose you need some n number of qubits, right? So so if you need n number of qubits to represent a particular, suppose Q0, Q1, Q2 to Qn minus 1, n number of qubits, and you have a strategy to encode this wave function of ammonia molecule here, right? So you choose certain way how to encode this problem. I'm not going detail to this part because that's an advanced topic. I'll come later. But in general, that's a vector, right? Sorry, that's a vector, right? And what is the dimension of this vector? Can anyone tell me if there are n number of qubits, right? What is the dimension of this vector represented here in this section? So what is the dimension here of this vector? Can anyone put in the chat box? We have to be very clear about the dimensionality, the multiplications, everything. Leave about the big hype sentences, anything about quantum computing. Very simple things, right? Exactly. 2 to the power n, right? It is the dimension of the quantum state here. So this is my size state here. Now I want to do something such that I can compute the ground state of ammonia molecule or the first excited state of the ammonia molecule, right? Or I want to know the time evolution of the ammonia molecule into different time, right? So I have to design a mathematical operator here, right? I have to design a mathematical operator here. I have to design another mathematical operator here. Sometimes it's just a Hadamard gate. There is some X gate and there is nothing, means identity, right? Sometimes you have to do some entanglement, right? This kind of thing. Sometimes you have to do ring kind of structure like this. So there is a R gate rotation and entanglement, this kind of philosophy, right? So every time you design various operator U1, U2, U3, so all they have 2 to the power n cross 2 to the power n dimension, 2 to the power n cross 2 to the power n dimension, right? 2 to the power n cross 2 to the power n dimension. Okay. So so that's why we are doing. So suppose you take only 10 qubits, right? Or 20 qubits, right? 20 qubits is not a big number of qubits for bigger molecules, right? And sorry, screen is not visible on my side, might be due to network problem. Can anyone else like comment whether you can see my screen?
Yes, yes, sir, it is visible. I think
Okay.
there will be some network problem on that side.
Yeah. So who they have problem, please rejoin. So that will be good. So suppose you need 20 number of qubits to just represent a particular molecule, right? So 20 qubits means you have 2 to the power 20, right? It's a huge number. It's a very big number, right? So big number just for the state representation here, 2 to the power 20, right? And you have how many matrices here? Suppose you only design a one quantum circuit, U1, right? And U1 has the dimension 2 to the power 20 cross 2 to the power 20 is another level of complexity, right? And this is just so your n here is 2 to the power 20, right? 2 to the power 20. And suppose you do matrix multiplication classically, suppose, right? So then your classical complexity says the matrix multiplication just to multiply into quantum operations, right? Suppose this is your blosphere, right, where you stand. your qubits basically reside, right? You represent, suppose this is your quantum information, right? It's psi, and there are 20 number of computational bases to represent that, right? I'm not drawing it like ket 0 or ket 1 because there are 20 such computational basis set, 20 0 to 21. So 20 0 to 21, and their combinations, right? 2 to the power 20 combinations. Suppose you are here, and suppose your solution is here. Suppose your solution is here. You have to reach here, then you have to do measurement, right? And so you do two kind of operation. First, you reach somehow here, and then you reach somehow using another operations here, right? So this is your path u1, this is your path u1, and this is your path u2. So how many calculations you do here? Your calculation is order of n to the power 3, right? So 2 to the power 20 power 3, 2 to the power 60, you can see, right? There's this many calculations you have to do just to multiply this operator times this operator, right? And for just to come from this state to this particular state, say this is phi state, right? So your ket phi is basically u1 times ket psi, right? And ket psi is 2 to the power 20, right? Is the dimension just for that with the 20 qubits. And this is 2 to the power 20 cross 2 to the power 20, right? So then what is the calculations for this vector and matrix multiplication is that just we learned, right? Order of n square. So 2 to the power 20 square, so 2 to the power 40. So just for the state evolution of 20 qubits, you need to compute 2 to the power 40 operations. If you have another quantum circuits, just for refinement, right? Um, operations. So if you do want to basically improvise your solution to reach from this point to this point, right? Using another level of time evolutions, right? So you have u1 times u2, right? So 2 to the power 60 complex computations you have to do. So u2, u1, and then psi will be your final state. Say final state is zeta, suppose this one, this particular state is zeta, for example, right? So what you have done to reach zeta? To reach zeta, you have done u2, u1, and psi, right? So you can see how many calculations you do with only 20 qubits, right? So this is how something we have to keep in mind, right? That when we design algorithm, right, what is the sense of dimensionality, where we do multiplication, where we do addition, where we do, so quantum computation in general, you don't do addition directly, right? You do multiplications, basically unitary multiplications, or you do tensor product, right? So that is the case, right? So just to, because why we do that, why we don't do addition, right? So to obey the postulate, right, quantum postulate, what it is saying, the probability of a state, right, if you do the integrations, right, integration from minus infinity to infinity or 0 to infinity regarding the presence of the wave function should be equals to 1. That means whatever be the consequence, sum of also all consequence equals to 1, right? This is the this is coming from the quantum postulate, right? And now you have discretized this part. So basically sum of all probabilities, right, px, if it is the probability of a particular instant, or the particular computational basis is pix, for all I, for all I, sum of all probability equals to 1, right? This has to be satisfying. Now, if I want to do this, and suppose my quantum state is ket psi, right? So this is before doing anything. Before doing anything, I mean, without applying any algorithm, suppose this is your initial state, right? And basically, what is the representation of the initial state? For the representation is basically alpha I, ket I, right? For I equals to 1 to 20 qubit, for example, right? So for 2 qubit, it is alpha 0 ket 0 plus alpha 1 ket 1. But 20 qubits is I equals to 1 to 20 alpha I ket I. This is your state representations. Now you have done two evolution. U1, you reach phi, and then another evolution you have done. So basically you reach zeta, right? So zeta is basically u2, u1, and ket psi, right? So your probability has changed. Suppose this is now beta j ket j, This is your representation for j equals to 1 to 20 qubit. Now I have to satisfy that sum of all beta j square equals to 1, right? If I want to get that, if this is the condition, if this is the condition, that means norm of zeta should be equals to 1, norm of ket psi equals to 1, right? Ket zeta equals to 1. If this is the situation, this will only happen if the, just 1 minute. This will only happen if zeta norm square equals to this u. Suppose u1, u2, u1 equals to u, suppose, right? Then u of this ket psi, right? This square. So this is my psi u star u psi, right? So now it is because the psi is a unit vector, right? Normalized. So sum of this ket psi square will be equals to 1, right? If and only if and only if u star u equals to identity, right? If that is the case, then only psi and psi dot product will be equals to 1, right? So this is the condition for unitary matrix. That means all the operation has to be unitary. Then this probability law will be obeyed, right? So that's why this is so important that all quantum operation has to be unitary in nature, right? Just to satisfy the probability law. Now if it does not happen, non-unitary case, so there are other additional things like the tomography and other things are there for this open quantum system, when the environment basically impact the quantum circuits, and also we'll look at those picture next week. So with this, I basically take a break of 5 to 10 minutes. So you can, if you have any question, you put in the chat, or you can take a break. So thank you. I think square is not written, should not be here. I just uh, wrote these equations this way. Is the screen visible now? Can anyone confirm? And
Yes,
just
sir, it is visible, sir.
yeah, some of the audience are saying sometime there is problem. I was just checking if it is my issue.
No, no, sir. It is
Yeah,
visible now.
yeah. So let's start maybe the second part. So shall I start, sir? Now?
Yes, yes, sir.
Yeah, sure. Thanks. So now, as per the if we see the syllabus, there are major portion is on the matrix decomposition techniques and the matrix inversions, right? So this part is important. Uh, Matrix inversions method. So there are two ways we need to go. One is the analytic method, mostly the direct implementation method, and the second part is the iterative method, right? Um, so in the iterative method, especially the conjugate gradient, or also we call it as a CG method, right? Jacobi method, for example, right? There are other methods like Newton's methods and other various numerical methods, right? Iterative method or the numerical algorithm, right? So these are also sometimes called numerical method, right? So this part I'll be giving the Python programs because there is not much theory, right? Although some of the theory part is written on my notes, but I'll cover the analytic part mostly, right? So there are some underlying theory we need to understand, right? And those portions also be required to understand the quantum part, right? Because most of
क्वेश्चन
the
फिलिप
quantum,
सर,
yeah,
सर आपने अभी कुछ बोर्ड पे लिखा है क्या? एक्चुअली हाँ, now it is visible completely. Actually, it was
okay,
showing loading. Your audio was clear, but
clear. I
it
see.
is sometimes it is stuck.
Okay, maybe some lagging happening. Maybe I don't know.
Yes,
Maybe
yes, sir.
due to internet or so. Is it now
Mm.
clear or still there is some issue?
Till Jacobi method it is visible,
Yeah, I have
but
written till that only. Yeah,
yes, but still it is showing loading circle.
loading circle.
Means like it is loading like something.
Okay.
So you
So
please write something.
let me rejoin from the iPad part once more.
Yes, yes, sir.
Sometimes there are problems.
No
Okay.
problem, sir. It happens sometimes, sir.
Okay.
We cannot
I
control.
think maybe due to WebEx, because WebEx
Yes,
has some.
maybe
So
sometimes.
yeah,
Yes, sir.
because Teams, we often do these kind of things. MS Teams has a better thing. Yeah, WebEx sometimes do screen sharing, especially. It's an issue.
Yes, sir.
Mhm. Let me try once more. It's a PQ PTP.
This webinar is being recorded in summary.
Um, is it visible now?
Now it's fine, sir. Yes, sir.
Thank you so much. Sorry for the inconvenience.
No. Okay, sir. Yes, sir.
Yeah.
Yes, now it is properly synchronized.
Yeah.
Like you are drawing the line and it is showing it here.
Yeah, thank you. Okay,
Thank
so
you, sir.
I will be doing the analytical methods, various analytical matrix inversion methods. So, and the motivation is very clear. So for example, if you have a set of linear equations, right? Say a11 x1 plus a12 x2 plus a13 x3, right, equals to y1. This kind of equation we have solved in our childhood, right? A21 x1 plus a22 x2 and a23 x3, right, equals to y2. Similarly, a31 x1 a32 x2 plus a33 x3. So now if we just write the same thing in the matrix vector form, so basically a11 to a33, right? A1 to a21, a13, a2 to a23, and a31, 32. So this is a matrix A, right? And it's a 3 cross 3 matrix, right? And then the unknown variable like x1, x2, and x3. This is unknown vector, and this is y1, y2, and y3, right? This equation is common to almost every engineering and science discipline, right? Now, if we want to solve this problem, right? So then we are often interested if it is x and if it is y bar to find the x bar, right? What is x bar? And you will say it is A inverse y, right? So this is not always the case that you can directly invert this matrix. So once you go for the dimension n greater than 5 or greater equals to 5, I should say, analytically, once you go n greater equals to 5, it is very, very difficult. Analytically, it's impossible to solve these things, right? So you have to go for various iterative methods and all, right? Or the extension of various analytical methods to the iterative region, right? So especially solving the equation of order 5 and above, right? Polynomial equation and finding the roots, right? That is one part. Second part is if your matrix A has something is called the condition number of A, right? Health of the matrix, number of the matrix A, that is denoted by kappa, right? So kappa of A, if it is big number, then condition number is big is so basically Ka is denoted by lambda max by lambda mean, right? So the deviation should not be high between lambda max and lambda mean, right? If they are closer enough, then the system has a good health. If it is the condition number is poor or the deviation between lambda max and lambda is very much, then the matrix has ill conditioning problem, and computing this A inverse has serious issue to compute that, right? This is the second part. Third part is, suppose my A matrix had some dimension if m cross n, and m and n may not be equal, right? So it's a rectangular matrix. Rectangular, I mean, you cannot invert a rectangular matrix, right? But suppose I have an engineering process, and the process is something like this. I am sending some information and I am receiving it, right? Out of it, I'm sending X, I am getting Y, right? And then if I am getting Y, and if the system is A, right? So then always it is not expected that the system is a good condition system or it's a square system, right? or it is a smaller dimensional system. It can be large dimensional, it can be rectangular, it can be tall matrix, it can be fat matrix, depending on m and n, whether it's m is greater than n or less than n, right? So basically this A determines various characteristics, right? So what happens? One case is basically sometimes in some problem, so we know A and Y, and we want to calculate X, right? Sometimes what happens, we know the input, right? And we know the output from measurement, but we don't have knowledge from, so knowledge about the system is unknown. About the system A is unknown, right? So then you need to compute what is A, right? This is called reverse engineering, right? And sometimes you are given, okay, so sometimes both A and X are unknown, right? So when you only have some observation, right? You neither know the system, you neither know the input, right? For example, you just measure that, you just see that there is some earthquake, right? Now, what is the reason for the earthquake? What are the region affected by the earthquake, and what are the sources that impacted the earthquake, right? So both the X and A is unknown, right? In earthquake engineering, right? For example, wireless communication. So you transmitted some data, X1, X2, from two antennas, right? And you received just Y1 and Y2, but you have complete no knowledge about the channel, wireless channel, right? So you need to model basically wireless channel, right? You need to model the channel, you need to identify the characteristics of the channel, right? And the equation is same, y equals to A X bar. If Y1, Y2, you stack them like Y1, Y2, you stack them as Y, right? And similarly, you stack this X1 and X2 as X, for example, right? And you need to characterize this A. A is completely unknown, right? Sometimes what happens, is that you have a set of satellite receiver, right? And you are just getting some responses from the air, right? In the antennas that you are Y1, Y2, so on, Yn. This is the telemetry communications, right? Where you do not have knowledge about where from the signal is coming or about the channel and all, right? Similarly, in earthquake, suppose there are two, three sources, right? X1, X2, X3, right? And there is certain plates, right? And you need to design what is your A. What you are seeing, you are only seeing there is earthquake, there is earthquake, there is earthquake. Impact is some Richter scale, something more than 5 or 6 or 7, right? Y1, Y2, and Y3. Now you have to do reverse engineering to find the sources, the impact, or the characteristics of the region, plates, etc. Right? So this is very interesting, right? Even when we do machine learning stuff, right? You have certain input nodes, you have certain output nodes, right? So what you have input is a set of images, right? Set of images xi. Now at the output you have only two class, right? So whether it's a class number y1 or class number y2, right? You have lots of inputs, but ultimately you have to classify into two part, y1 and y2. So this is suppose sometimes known, y1 and y2 are sometimes known. So this kind of problem are called the classification problem. And you also know your neural network, for example, right? That is the A matrix you already know. If you want, I want to model it as a y stack of y as a stack of x, x1 to xn, right? There are many elements, right? X bar, right? And there is some x, a, right? And this is your y. And if you know that the responses y, what are the things? So this is a classification problem. Sometimes even you don't know the labels y and y1 and y2. You only have some knowledge about the network and the input. So you do problems known as the clustering problem, right? Clustering problem. So this way, this equation is so important, right? Across literature, right? Similarly, on the quantum side, sometimes you know the encoding, right? but you do not know the dynamics of the system. Dynamics is U, right? Input is get psi, output is get phi, right? This is your output state. It's a vector, right? Then you are doing measurement and you are getting certain probabilities, right? So basically from the probability you have some vector, say y1, y2 after multiple measurement, right? Ym, doing the expectation and all calculations. I'll come that part next week. But in general, you have an output, right? Sometimes you do not have any knowledge of the encoding scheme. You do not have some knowledge about the uh, of the system itself, right? So or the dynamics of the system. Sometimes you know the dynamics, you know the input, but you don't know what may be the consequent at the output because there is environment impacting and other things are there. So that's why this we need to have, or we need to know a tool, mathematical tool that can solve this kind of equation, right? So let's break this equation and just let's try to compute a inverse thing, right? Matrix inversion process, right? So I'll give a comprehensive overview so that you can take the detail from my notes. So I'll not cover each and every topic because it will take a semester to cover the thing. But yeah. So one first method is the Gauss-Jordan method, right? Another thing is that A matrix has say n cross n element, right? M cross n or n cross n in general, right? So generally m cross n, but suppose m equals to n and you have n cross n elements, right? And then to basically how many elements are there in the matrix? So there are n square elements, right? Elements in this matrix, and there is m into n elements in the matrix A, right? So anything you do, whether you want to multiply A into B, right? So you have to multiply over n square element in A and n square element in B, right? And the complexity we have seen matrix multiplication is order of n to the power 3, right? How we do the multiplications between two matrices, right? Similarly, in quantum, there are operations you have to do like the commutation operations, like A B commutation equals to A into B minus B into A. And you need to check whether two quantum operators are basically commute or not, right? For example, the position operator and the momentum operator, right? These two operators. So you will see they do not commute. That means the x bar, p bar minus p bar x bar is not equals to 0. If it is equals to 0, we say the operator A and B commute. If they're not equals to 0, we say they do not commute, right? That position and momentum, they do not commute. Okay. So basically it is not equals to 0. In fact, it is equals to some I bar H and there is some factor, right? So this kind of operation we'll be doing, but in general, you can see these are typically matrix multiplications, right? So now, if you want to calculate the basically n square element, right? So that means I have this many elements. If it is a 3 cross 3 matrix, so that means here 3 square, that means 9 elements are here, right? Now, can I do some sort of conversions? Later, I'll see that is there a way that I can minimize or I can represent the matrix in a better way? For example, is there a way that I can represent my matrix only in the upper diagonal case like this and rest at 0, for example, this way? Or can I represent it this way? Um, is a tridiagonal way? Or can I represent it in this way that only there is diagonal elements and rest are 0? Because for 0, I don't need to compute as such intelligently if you design the algorithm, right? So because every time you are reducing the operation instead of n square element operation to some reduced number of operations, right? Because here it is less than n square. It is in fact the diagonal representation takes operation only on n elements, right? Only the diagonal elements, right? So these are various mathematical ways how we can basically intelligently do computations, right? And let's start with the very beginning, that is called the Gauss-Jordan method or Gauss-Jordan elimination method, right? So what we do is something like this. So if you have a matrix A, then first we do an augmented matrix A and I. A, suppose A is n cross n, so identity is also n cross n. Then we try to do certain arithmetic like calculations like row exchange, column exchange, and their basically permutations, right, of operations. And we try to reach something like this. This will become identity and this will be becoming A inverse, right? So this is one method that typically we do for this Gauss-Jordan elimination method. So basically identifying the pivot element and all. So I'll be sharing you the notes and example for more details. Just I'll focus only on the complexity part for today. So if you do this augmentation basically has order of n square operation. If you write in the n cross n way, like A has n cross n, identity has also n cross n, so it is order of n square, right? And the second step is the pivoting step. What is pivoting? Pivoting is if you have this kind of matrix representation, first target, say for example, if you want to do this kind of process, for example, this one. So our target is to make this matrix to identity matrix, right? And whatever operation every time we perform and stack them in a operation or a matrix, so that will become the A inverse. So first target is basically you uh, normalize this vector and target this element first and try to make it basically ultimately you have to bring it to 0, right? So first you normalize it to 1 and then basically subtract with some row such that it becomes 0. Then you target this, then you target this. So these are called the pivot elements, right? To make this ordinary matrix to the identity matrix form, right? So these are certain operation important. So pivoting operations, if you want to do, so it also takes order of n square comparison in total. And number of row operations, row exchange operations, we have to do order of n to the power 3. So the total operation is order of n to the power 3 in this method. Okay. So partial pivoting improves the stability but does not guarantee if the matrix if the health of the matrix is bad. If it is good, then fine. If the condition number is good, then this method is okay. But if the condition number is bad, that means it's a ill condition matrix, then this kind of operations might not be scalable, right? So this is one way, just directly inverting a matrix using the Gauss-Jordan method. Second is the LU decomposition. Now I will also say which method we should do when, right? So I can also sometimes break this matrix to this way. This is L, this is U, this is A. A is ordinary, right? Suppose there are 9 elements. Can I do this way? That I have a lower triangular matrix like this, and I have a upper triangular matrix like this. Rest are 0, right? So now you can see how many operations you need to do on L is basically almost like half, rest are 0. And on the U side also you need to do almost half, right? So this is just representing in the lower triangular form and upper triangular form. So you are representing a matrix into the triangular form. So triangular form means earlier you had, if you have a square form, right? So you are making square means sorry, you are from a square you are making a triangle, right? Means almost half of the almost half of the number of elements you need to operate, right? So by doing this LU decompositions, we basically have by these decompositions you have 2 by 3 n to the power 3 is the complexity. So often we read for large n we absorb this 2 by 3 constant. So it is also order of n to the power 3, slightly less than the ordinary Gauss-Jordan method, but in general it is also power of 3, right? So this is often this is used in MATLAB for our ordinary mathematical inversion problem in MATLAB and various Python package like Matplot, like the NumPy and all. LU decomposition is very common, right? Now, suppose my matrix is something like this. Suppose AX equals to B. Suppose A has M cross N, this has n cross 1, and this has m cross 1. This is my equation. So this is my linear equations, right? This is my linear equation. Now, of course, I cannot calculate this A inverse directly. So whether there exists A inverse or not, so that's a question, right? Because it's a rectangular matrix, I cannot directly invert it, right? So LU decomposition basically it's for any A, right? You can decompose into lower and upper part, right? But in general, for M cross N, this kind of matrices, there is a method called the least square method. We'll come back to the least square method from error when we'll try to mitigate error in quantum circuits and all from the probability using the probability principles. But now just stick with the algebra part. So our equation is X equals to B, right? And because X equals to B or Y, whatever you wish to write, X equals to say Y, right? And we wish to calculate this X. So out of this, we want to get this X hat vector, right? So if you have problem to visualize this, just I'm writing it as this way, right? So if I want to calculate this X hat, right? And then and directly I cannot do A inverse directly I cannot do, right? Because it's a rectangular matrix, as well as the condition number and other things will be there. But for now, it's just an ordinary matrix, right? So there is, of course, there might be some error in the calculation, and I need to minimize this, right? So this is basically the actual way of solving this equation. So how we can minimize the solution. So you can use any iterative method to solve this, or you can simply you can minimize over X basically, and then you can get the solution X hat by using calculus, right? Using calculus, you can solve it, right? And there is an alternate method also. That's the called mathematical projection. So any solution you get, suppose this is your vector, right? Y vector, right? And yeah, on the first day yesterday we have seen basically if you want to get this basically this the solution given this vector y, so you can project it to the column space of A matrix. That means y bar to here. So it is AX axis, okay? And this if you can project it, so this is your solution basically, solution space. And if you can project here, this is the error part and this is the estimate part, X head, right? So basically that means I need to find a projector P such that if I multiply on the Y transpose, I get the solution X hat, right? This is one solution. So how to design the projector? So I'll show how to design projector, but I'll suggest to all of you to have a look of the lecture series by Gilbert Stang, and that is amazing how to prepare reflector, projector, rotator, and all those stuff, right? So it is a bit detailed, but you will amaze how to design this stuff. So for now, so I have the equation Ax bar equals to y bar, right? And suppose let us multiply A transpose left hand multiplication A x bar equals to A transpose y. So I pre-multiply A transpose in both sides, right? So what happens immediately? So A has the dimension m cross n, right? Now it becomes, if it is A m cross n, then it becomes A transpose A, right? So A transpose A will be n cross m cross m cross n. Immediately it becomes n cross n matrix, right? This side. And now it becomes a square matrix, good for inversion, right? So, but I have to calculate x bar, right? So I have to remove this part. So what I will do, A transpose A whole inverse. I pre-multiply this part with the existing matrix A inverse A x bar, that is equals to A transpose A whole inverse A transpose y. Again I pre-multiply with A transpose A, just to so yesterday I mentioned the lecture series by Professor Gilbert Strang, and maybe you can have a look. So let me write in the chat box for this. YouTube will get YouTube 35 lectures are there. So so those are very basics lecture. It is good if you can just have a look in the lecture series to the lecture series. Yeah. So now basically what I get is so this part is basically, suppose A transpose A is B, right? So you have B inverse B, right? So B inverse B is identity matrix, right? So that means this entire part becomes identity. Identity times X bar becomes X bar, right? So your solution will be X cap or X bar equals to A transpose A whole inverse A transpose Y. Right. So this is this A transpose A whole inverse, that is a n cross n matrix, right? Times the A transpose, right? Which is a n cross m matrix, right? Which is a n cross m matrix. So this is not actually an inverse, but it does the objective of an inverse. That's why it's called the pseudo inverse. Pseudo inverse of the matrix A. Now, instead of solving Ax bar equals to y bar as x bar equals to A inverse y. So this is direct solution, but you cannot get it for rectangular system. This is good for square with good condition number, right? With good k. But if it is a rectangular matrix, then Ax bar equals to y, you have a better solution, or you have a solution at least, that is X had approximate equals to A transpose A whole inverse A transpose y bar, right? So this is the pseudo inverse part, pseudo inverse of a matrix A, and now you have a solution, right? So what is the complexity with this? The complexity is order of mn square plus n to the power 3, right? So so this is the complexity, and if n equals to if n equals to m and n, they are equal, then it is roughly equals to order of n to the power 3, right? So the condition is, this method works, the condition is that the condition number of A transpose A, this matrix, right, that has to be good. If kappa is bad, if the condition number is bad, then this least square method does not work well, right? So the definition of condition number, I said already, but let's repeat it. So condition number K of a matrix A is the norm of this matrix times norm of its inverse. Okay. Norm of its inverse, that is equals to, this is also defined as, this is also defined as sigma max by sigma mean. Sigma max is the maximum singular value. And this is the minimum singular value. Minimum singular value, right? And this is also defined as lambda max by lambda mean. This is the maximum eigenvalue and this is the minimum eigenvalue, okay? Now what is eigenvalue, what is singular value, I'll come, no worry. So if k is less, right, if k is less, then at least less than 4,000 or 3,000, there are some numbers, right? If it is less, then the health of the matrix is good. If the deviation is much, lambda max and lambda mean is much, then the condition is condition number is ill condition, or the condition number or the system is ill condition. Let me give an example, right? So if you have good time in life, right, good time in life, and you measure the happiness by lambda max, right? And if you have bad time in life and you measure the sadness by lambda mean, right? If this is lambda max is the index of your happiness, lambda mean is the index of your sadness, right? And if your happiness by lambda max, that means happiness maximum happy, and the maximum sad or the lambda mean, right, if the ratio is closer to 1, right, then you are good condition. Otherwise, if you are very happy in good times but you are broken down in bad times, right, that means you are not good conditions, right? This is very true for our health of a human body or health of any system, right? So that's why this lambda max and lambda mean is pretty good. One good part is for unitary matrices especially, right? Unitary matrices, which are the like the founding or foundation of quantum computations, right? All the operation in quantum computations for the isolated quantum systems, they are unitary matrices. And right, quantum computing, all operations are unitary, right? They have lambda has a nice representation, e to the power I theta, right? So that means basically all their lambda sits on a unit circle like this, whether it is lambda max, whether it is lambda mean, any other eigenvalue, right? So all they have like lambda 1 equals to say e to the power I theta 1, and lambda n equals to say e to the power I theta n. That means all of them has amplitude equals to 1. Only they have different phases, right? Different phases. So if you put the definition of a condition number for a unitary matrix, you'll see 1 by 1 equals to 1. So health of a unitary matrix is very good, excellent, right? So in just by direct definition, but I haven't considered the phase factor here, right? So there are other things to compute health and all, right? So now this part is we have to take care when we calculate the inversions, right? Um, now let us see some more decomposition techniques, right? One is called the QR decomposition. So we are starting various factorization technique, okay? Matrix factorization techniques. So suppose we have a matrix like this. Right. Suppose this matrix is A, okay, and A has suppose 3 column vectors, A1 bar, A2 bar, and A3 bar, right? So A bar, for example, A1 bar has the element like this: A11, second row 21, and A31, right? Like this, so on. Now, what we can do, I can always break any matrix A this way. So I can normalize this vector, right? And I prepare this A2 to some vector. So I prepare A1 to some Q1 vector, right? Where Q1 vector is just A1 vector by norm A1. That means I have normalized this vector, right? And I get Q1 like this, the first column. Second column, I create somehow, I do mathematical operation such that I create a Q2 vector, right? Such that Q2 is perpendicular to Q1, right? Similarly, I prepare A3 to Q3 such that Q3 is perpendicular to Q2, perpendicular to Q1. This way, using mathematical projection operation. How to do that? There is detailed note. Some part of the notes are available on my website, and other part of the notes I'll be sharing. Don't worry. So, what effectively I'm doing Q1, Q2, and Q3, right? So all these Q1, Q2, Q3, they are orthogonal to each other, these vectors, as well as they are all normalized. That means Q2 is a normalized vector, Q3 is also a normalized vector. So this particular matrix is known as a orthogonal matrix. Orthogonal matrix. Orthogonal matrix. Now, if you do that, so every time when you do the mathematical projections, right? So this occurs only if there is an additional part coming as a upper triangular matrix like this. Rest are zero, right? So this is called this is just an upper triangular matrix R, okay, and this is known as the QR decompositions. QR decomposition. So this is the upper triangular matrix. Now, for a orthogonal matrix, right? So yesterday we gave the definition of orthonormal vectors, right? Basis sets, orthonormal basis sets, and these are critically important for quantum computing to represent your quantum state vectors, right? So because these are orthonormal, their dot product will be equals to 0, right? That means Q transpose Q is a identity matrix, right? Is a identity matrix. Okay, so this is a well structured matrix, but this R is a upper triangular ordinary matrix. But the good part is earlier you had n square elements, right, in A, but you have almost half elements in R, right? Now you can ask me what is the utilization of QR decomposition, right? What is the utilization of QR decompositions? So we just learned that for any ordinary matrix, whether it's a rectangular matrix or it's a some general matrix, the solution of a linear equation is x hat equals to A transpose A, right? Inverse and A transpose y, right? This was my solution. And in general, this is written as a star or a dagger y, right? Pseudo inverse a plus y or a dagger y, right? This way. This a plus is equals to these three terms, right? So now we just learned that a can be written as qr, right? Qr decomposition we can do for a. Immediately what happens is this a transpose, right, will become qr transpose. That means r transpose q transpose. Then a transpose a becomes r transpose q transpose sorry, q and r, right? So this is for the A transpose part and this is for A part. Now Q transpose Q is identity matrix just to define. So it becomes R transpose R, right? So A transpose A, how many elements are there in A transpose A? There is n square element in A, there is n square element in A. So how many operations you do for A transpose n to the power 3, right? You already minimized half of the element in R, right? So almost half of the operations you already reduced for R transpose and R. So altogether the operation reduced very efficiently from A transpose S to R transpose R, right? So basically when you do A transpose A inverse, right? That means you do R inverse, right? R inverse or R inverse R transpose inverse, right? Something like this. Okay. So altogether, I can write this equation x hat equals to A transpose A whole inverse A transpose, right, into y. So that means that is equals to, if I put all in terms of A, so A transpose A whole inverse is R inverse and R transpose inverse, and A transpose is basically R transpose, right, and Q transpose, right. So that means into y. So this part becomes identity. So it is R inverse, Q transpose, and y. So simplified, right? Now calculating exact. And this is just a orthogonal projection. So basically, Q is a orthogonal matrix, right? Orthogonal matrix. So that means suppose this is your y, right, and you are basically multiplying it with q transpose, right? So it is just basically converting this y to some other y here, say for example y, such that y is represented with the basis of the column vectors of q, which are orthonormal basis sets, right? So this is just similar to r inverse, say this is z vector, where z vector equals to the q transpose y bar. So why it's some observation? That observation you are not very much sure how to represent what is the best representation for y. You just convert it to the orthonormal basis with the orthogonal vectors q, right? And your inversion becomes so simplified. X hat equals to R inverse Z bar, right? So this is just a application of QR decomposition of a matrix. And you now see, instead of these complicated all the calculations, you just need to do these things, R inverse, which is a upper triangular matrix. So you have saved a lot of memory, right? Lot of space and time, right? So homework is here. Here you have a homework. Suppose a equals to 1, 2, 4, right? 0, 0, 5, and 1, 3, 6. Calculate the Q and R by hand. Okay. In MATLAB, the solution is basically very simple. Just you need to do QR of A equals to C comma D. This is the command line for MATLAB. But you can first do hand calculation, then check with the MATLAB code. If you do not have MATLAB, you can use the Python NumPy library. Okay, lean ALG library, and you can call this. Suppose you call this library as NA, and you call NA.QR of A, and you define the A matrix as suppose C, D. This is your Python code, and this is your MATLAB code. Okay. So with this, I stop here for another 5 minutes, and I'll come back and we'll visit the SVD, QVD, and we'll see their implication on the quantum computing. Please take a break of 5 minutes, and please let me know if you still stuck on my screen or if you face any difficulty. Can you please let me know, or is this fine?
Yeah, participants, if you have any questions, you can mark it. You can put it in the chat. Otherwise, we'll take a 5-minute break, 5 to 10 minutes, and then we'll come back.
Yeah. So shall we start maybe?
Yes, sir.
Yeah,
We are
thank
just,
you.
I was about to say the same. Yeah, we can start. Thank you.
Thank you. Yeah. So just let me. So we just have seen the QR decomposition techniques. Now we'll move to some other mathematical decomposition techniques, especially we will reach to eigenvalue decomposition part. But eventually there are some advanced topics due to limitations of the syllabus and other things. I'll take those parts in a later QT. For example, the Krylov method, Arnoldi, etc. In a upper part. Okay, so now so we are talking about the matrix inversion techniques, right? And we have seen that just by doing the keyword decomposition, which is very common, and so typically when you give certain basically problems to MATLAB, when you solve directly on MATLAB, right? Or the NumPy using certain solutions. So you see, there are two things. One is you give the solution, say y is your variable, and you basically do this a slash this thing x, right? Or sometimes you denote as the inv a times x, right? This way you write the pseudocode in your MATLAB, right? So this is the direct inversion process. But if you want to go the least square solution, so you can also write the command line as PINV of A, pseudo inverse of A times the X. So I wrote the opposite, so it should be actually something like this. So this should be X equals to this way, right? Right. So this way, this is the comment for pseudo inverse computation on MATLAB. If you are using NumPy libraries, so it just you just need to associate the library linear algebra and put this extension here. Say for example, n.pnb, n.pinv, etc. Right. And then there is a direct way you can just direct write this way \y, and this does this backslash basically compute directly the pseudo inverse in MATLAB directly, right? So sometimes we put backslash dot for the if dimensionality mismatch between A and Y, right? Then also these are certain mathematical let's say prompt or comment line for MATLAB code if you want to solve linear systems, right? And MATLAB internally does the keyword decomposition, even if you do not say often, just to reduce the computational memory or RAM. Just to efficiently use the RAM of your computer, it internally decompose the A into QR, then compute this X equals to the pseudo inverse of A times the multiplication Y, right? So this is something important. And now we'll move to another decomposition techniques, which is called the Cholsky decompositions. Okay, there are basically one more decomposition which is not that important in quantum computing, but you can keep a note, that is called the polar decomposition. Okay. This is less used but also important, polar decomposition. You can decompose a matrix A into U times P, where this U is basically a unitary matrix, right? This is a unitary matrix, and this is basically P is a PSD matrix. Okay, PSD matrix, a positive semi-definite matrix. iPad. I need to connect it to power. Just give me 30 seconds. Yeah. So positive semi-definite matrix. So what is a positive semi-definite matrix? If you have a vector x, and then if x transpose px greater equals to 0, then this x is a vector, some vector, okay, some vector which is compatible for the multiplication with the matrix P. Then we say that P matrix is called a PSD matrix. P is PSD. Now you may forget this definition. So forget the definition. If the eigenvalues are greater equals to 0, right? Then this is a PSD matrix. Okay. Positive semi-definite matrix. Is lambda strictly greater than 0, we call it a PD matrix. Positive definite matrix. Okay. And if it contains the 0, then positive semi-definite matrix. Positive definite matrix. And unitary matrix we already know. If u star u equals to identity, or u star equals to identity, then we call the matrix U as unitary matrix. Okay. Okay, you may forget this definition, but simply consequence of this is basically this is only possible if U star equals to U inverse, right? If this is the condition satisfied, very smaller condition, that means you post multiply or P multiply with U inverse, right? So with U, so it is equals to U inverse, so that identity, right? Same thing. So how to remember? If U star equals to U inverse, right? Then we called it is a unitary matrix. This is also called self-involuntary matrix. And if U star equals to U, right? Then we will call it as a Hermitian matrix or symmetric matrix. Hermitian is for the complex case, Hermitian matrix. Okay, this is the definition of Hermitian matrix. This is the definition of unitary matrix. Okay, so very simple. Yeah, this is called self-involuntary, and this is just a symmetric transpose equals to the same matrix. Okay. So this is the polar decomposition. If you can if you have a matrix A, you can always decompose into U into P, a positive semi-definite times a unitary matrix, polar decomposition. Okay, although it is not that much utilized in quantum, but of course it has many utilizations in wireless communications, radar, signal processing, control system, for various phase analysis, right? Control phase and various antenna characteristics analysis. So polar decomposition is an important tool. Now, if so, this is what we have discussed for all ordinary A. For ordinary A, for ordinary A, we have learned many tools, right? Now, if okay, let's continue the ordinary and see another two decomposition. One or two. The matrix A also we can decompose into any ordinary U. We can decompose into U sigma V transpose this way, right? Where U star equals to identity is a unitary. V star is also identity. That means it also a unitary. Both are unitary matrices. And sigma is a diagonal matrix. So there is a research paper in 1967 or 1970, in 60s or 70s. The paper is commonly known as the GKR algorithm. Okay, and this is the author Golub, Kahan, and Reinsch. Okay, these three mathematicians wrote a paper how to efficiently compute this U sigma and V transpose. Okay, and this is the paper the author Golub. I referred the book yesterday, right? The same author. And this algorithm, GKR algorithm, you can see how to basically reach from ordinary matrix, like any ordinary matrix, to a diagonal matrix. When I say any ordinary, then SBD you can apply, not EVD. Okay. EVD needs additional condition. I'll come. So if I do SVD, singular value decomposition, I'll be reaching to sigma 1, sigma 2, and sigma 3. All rest are 0. And there is U and there is V transpose, right? These are unitary, there is no issue, right? But this is a diagonal matrix. Now, earlier you were operating on n square element. Now you will operate only on n elements, diagonal elements. So this is so efficient, right? Representation of the matrix. So this makes our life very smooth and very the computation is much less right here, because you need to only compute on this sigma. This matrix is sigma, right? With the element sigma 1, sigma 2, and sigma 3. Important to note that all such sigmas are belongs to real number set. Okay, they are never complex numbers, right? And also singular values are typically non-negative. Okay, so they can be in general greater equals to 0. So these are two important properties. Okay, and for eigenvalues and singular values comparison will again come back, but let us discuss the complexity part, because we are doing the complexity calculations things, right? And then again we'll come back sometime on the SVD part, right? So so basically earlier we were doing this x hat calculation like matrix inversion thing. That was A transpose A whole inverse A transpose this Y, right? And now you put everywhere this thing, um, everywhere instead of this A transpose. So for example, A is your U sigma V transpose whole transpose, right? Then A U sigma V transpose. Then you have U sigma V transpose whole transpose, right? And Y bar. Can someone simplify these things and let me the answer? So let us do together. Single variable, can you give me some information? Single variable, multivariable, quantum state. Multivariable quantum state basically, okay, two-dimensional encoding. These are like much advanced topics. So typically, either you have to go density matrix approach or two-dimensional encoding technique. So this is outside syllabus. Maybe next week I'll try to discuss a little bit, but yeah, these are very advanced things. Yeah. So V transpose of transpose will become the V, right? And then sigma transpose, right? And then U transpose, right? And this becomes U sigma and then V transpose, right? Um, so this is the first part, and this part will become V sigma transpose and U transpose and Y bar, right? Then this is identity, right? So V sigma transpose sigma diagonal times diagonal, this one, right? And this is V transpose V, right? Sigma transpose U transpose Y bar. Again, this V transpose V becomes your identity matrix. So you left with V sigma transpose sigma and then sigma transpose, right? So there was one inverse also. I forgot to keep the inverse most likely. So there is one inverse, right? So I made some mistakes. So ultimately, you can see this will be reduced. We need some more time here. So this will become identity. Then after doing the inversions thing, some of the other elements like, so basically V inverse equals to V star, right? This kind of property you can implement here. And you will be left with only some elements, right? Only some sigma star, sigma whole inverse with sigma, this kind of thing with some Z bar, for example. Okay. So there is like two steps calculations we need to do, and we'll be ultimately reaching here, and all these are diagonal, right? So the calculation is much simplified here. So I need to only do operation on only these n elements, right? N elements matrix inversions, right? So for example, if you want to calculate the sigma inverse, right? So sigma inverse, so sigma is basically your these matrix sigma 1, sigma 2 to sigma n. Using the singular value decomposition, you have diagonalized it. So sigma inverse will be only 1 by sigma 1, 1 by sigma 2, and so on, 1 by sigma n. So this is very simple. So the inverse calculation is just by fraction, computing the fraction of number, something like that, right? So basically 1 by sigma 1, 1 by sigma 2, and so on. So basically computing the x hat to using the SBD approach, right? So earlier we have done three approaches, one by QR decomposition, one by SBD approach, and one by directly least square method, right? Least square method is basically A transpose A whole inverse, this A transpose, right? This is the pseudo inversion thing. And then we just did the QR decomposition above. So the QR decomposition, when we did, what was the solution? Let's look at to that. Yeah, is the R inverse Z, right? Or R inverse Q transpose Y. R inverse Q transpose was the solution. R inverse Q transpose was the solution. R inverse Q transpose was the solution. Now you have something as a function of sigma. I mean sigma transpose sigma whole inverse, something like that. So this is called this is called a direct least square inversion. This is called a QR based pseudo inversion, and this is called, there is a special name that is called Moore-Penrose pseudo inversion. And this is exactly what is used in some algorithm called HHL algorithm, Harrow-Hasidim-Lloyd algorithm for solving linear system on a quantum computer. On a quantum computer. So this is for all the ordinary matrices, right? Means whatever be the A, I can apply the SPT, right? Yeah, I missed the in-person part, so there was some more calculations I have to do here, right? And then I have to break the equations and just simplify it, which will be a function of sigma, right? Sigma matrix, yeah, diagonal matrix. So now let's move to for the basically some better matrices. Better in the sense better structured matrices, or the matrices which have better properties. So earlier A has no condition. Now A is a PSD matrix. If A is a PSD matrix itself, that means X bar transpose X AX greater or equals to 0. This is by definition, right? Then A matrix has a very good decomposition, and that decomposition is known as Cholesky decomposition. So just 1 minute. So A matrix, you can, if A is a PSD matrix, then you can represent as LL transpose. So what is LL transpose? L is a lower triangular matrix. So earlier we have seen if A is any ordinary matrix, we can decompose into LU decompositions, right? For any ordinary A. But if A is PSD, you don't need to compute this U. You just need to compute L. There is no need to compute U. So then A can be decomposed at L transpose. So you just need to focus on this part, because this is just a copy of the memory. No additional computation is required for this part, right? So basically it's a lower triangular matrix, and the second part you don't need to calculate, just a copy of the memory of the first part, right? And transposition. So basically so this is a much structural decomposition of A, if A is a PSC matrix, and this particular decomposition is known as Cholesky decomposition. And by doing Cholesky decomposition, we can save a lot of memory, right? For solving certain problems. So at the end, towards the end, I'll give a summary of solution. So basically, if you do Cholesky decomposition, so roughly it takes 1/3 n to the power 3 is the complexity for n cross n matrix A. Okay. So this is by Cholesky decomposition, say CD. If you do LU decomposition, it takes almost 2/3 n to the power 3 is the complexity. If you do QR decomposition, the complexity is almost 2 to the power 2 into n to the power 3, right? This is the ordinary QR decomposition. Now, if you do, so basically QR decomposition, sorry, sometimes this WebEx has strange behavior. Okay. Sorry for this. Is this visible now? There was some problem.
Yes, sir, it's visible now.
Yeah, thank you. So QR decomposition also, there are ways how we design the QR algorithm. So QR algorithm means basically A matrix, you are decomposing into one orthogonal matrix and one upper triangular matrix, right? This orthogonal matrix designing from A can be via projection approach. So which is standard, like Gram-Schmidt method, projection approach. With that approach, you have the complexity 2 into n to the power 3. But there is another method which is called the householder approach. He is another mathematician, householder approach. It basically takes the approach of mathematical reflection. Okay, mathematical reflection approach, and you can reduce a little bit of the complexity to 4/3 n to the power 3 is the complexity, roughly, approximately. So these are various ways how you can solve matrix computation, like the computing not only the inverse of a matrix, but various cases like multiplication and other things, how you can utilize memory, right? How you can save the memory, because that is important. Now, the most important part is the EVD from the quantum computation concept. This is called the eigenvalue decomposition. Now, always best thing does not come for free. Every best thing always have conditions, right? So condition for eigenvalue decompositions. So in general, for any normal matrix, if a matrix A is normal, EVD exists. Okay. So what is normal? So normal is if A transpose A equals to A transpose. If this is the condition given, if this is given, A transpose A equals to A transpose, then we call that A is normal. This is a much like concrete assumption or condition to make to EVD happen, to get the EVD happen, or the matrix to be diagonalizable by eigenvalue decomposition technique. Okay. A simpler condition is if A is Hermitian, that means A transpose A. If this is that means that basically symmetric matrix or A Hermitian equals to A. This is also written as A star equals to A, right? Same thing. So this is called the Hermitian condition, right? Hermitian condition. So symmetric and Hermitian condition are loose condition, but more mathematically concrete condition is a normal matrix consideration. That means at least A star equals to A star, then this EVD exists, right? So now all the physics based formulas, right? Whether energy, momentum, all the physical phenomena, right? So you have seen the dynamics is represented by something called Hamiltonian, right? Hamiltonian. And the Hamiltonian is basically a Hermitian matrix in general, but there are non-Hermitian Hamiltonian exist, but in general, physicists consider Hermitian Hamiltonian for isolated quantum system, Hermitian matrix, okay? Because if they are Hermitian, then basically I can always do eigenvalue decomposition. But if they are not Hermitian, still I can do eigenvalue decomposition by using the normalization normal matrix condition, this one, right? So if it is if they are Hermitian matrix, right? If they are Hermitian matrix, then the eigenvalue of those matrix A will be real, belongs to the real numbers. Okay. Will belongs to real number. So for example, this is the I del t, right? H bar. So H bar also I can write it the left side. Just 1 minute. I H bar del t. So this is basically energy operator. Okay. So so if I apply the energy operator on the wave function, right? I should get back energy as a quantity, right? Energy as a quantity E1. So this is a scalar quantity or observable scalar. So this is you have seen the energy spectrum of hydrogen, right? So what does it mean? Basically, this is an operator, right? And whatever value you get is an eigenvalue of that operator. Okay. And to get this eigenvalue as a real quantity, physical real quantity, whether energy, momentum, or space, right, a position of a particle, right, you need a corresponding Hermitian operator. So this is a differential form of the Hermitian operator, but in general, you can discretize this part and get the matrix representation of the Hermitian matrix, right? So that's why in the Schrodinger equation, left-hand side, you have seen this, right? And this is exactly giving you the energy of a basically particle or wave, you can say. So that is basically a real quantity, means the corresponding operator is a Hamiltonian operator. Now, when we solved these equations, right, and we came up with something like this. So this equation is equivalent to. So right now I'm telling the physics part, but I'll again come back to the matrix algebra. So I H bar del t psi t, for example, and we get basically H of psi t, right? So of course you can break this H into kinetic energy part and potential energy part for the chemistry or physics problem, but in general this can be any engineering system which can eventually you can model as a quantum mechanical phenomena, right? So that was the greatest invention or the consideration by the Broglie, right? So de Broglie we say often, the spelling is the Broglie. So the Broglie in his thesis here, he showed that not only photon, but any physical matter on Earth or any particle on Earth has a wave nature, right? So that is called the wave particle duality, right? Wave particle duality. About 1926 or 7. something like that. So basically, his invention was basically not only photon, but any particle on Earth, you can basically they have a wave nature. If they have a wave nature, they have a lambda, right? And if they have a particle nature, they have a mass, right? And so better than mass, you can see it has a momentum, right? So momentum and lambda. So you can relate those two phenomena, right? And so if that is the case, then this Hamiltonian you can always design for any natural phenomena. It may not be always it has not to be always the physics or chemistry, but in general it can be any biological phenomena. For example, suppose you are studying the DNA, right? And you want to find the Hamiltonian for a DNA dynamics, how the DNA basically RNA moves in the cell, right? So you can always find the Hamiltonian for that, right? So just by using the concept given by de Broglie. Okay, so the concept is so left hand side is an energy operator, right? And this equation is equivalent to this E of chi equals to H of chi. Now forget about chi t. Just name them as x. Just name them as x, some vector, right? And this is some instead of differential equation, just take it as a, right? And instead of h, take it as lambda. So what we get, x equals to lambda x, right? And this is what, this is our eigenvalue equation, right? So we know this from class 12. Eigenvalue equation. So quantum mechanics is nothing but eigenvalue equations, right? So in general, with all the assumption, right? Isolated quantum system, etc., and all. So this is the energy representation or the quantum dynamics representation with respect to time, right? This is same as the eigenvalue equations, right? And typically so you can find many such represent. So basically what how did I get this? So I can always find some this I can always represent this GIT wave function using quantum superposition to the eigenbasis, right? Ci some xi, right? Or xi are the computational basis sets or the eigenbasis set, right? Eigenvectors, right? For all I. So you can represent the wave function into many basis sets, right? For each basis, for each such x, suppose you get some suppose you get this operator a times some x1, and you get lambda lambda 1 x1, right? For another x2, another eigenvector, you get a times x2 equals to lambda 2 x2, and so on. You get a times xn equals to lambda n xn, right? So at how many solution you get? You if this if it's a full rank matrix, you get n number of solution. If A is full rank, right? So then you get n number of such solutions, right? Also you can relate this to the linear equations, right? But the beauty is the part here x and x. So what it does, there is a geometrical interpretation, right? Interpretation. Suppose this is your vector, right? Let me take some colors. And you apply a matrix here. And suppose this is your you apply a matrix here, right? A matrix A you apply to the vector. The vector is say x, right? Now what can happen, what actually does a matrix does is basically either it changes its direction of the vector, or it does stretching of the vector. These are the two main thing a matrix does on a vector. So when you basically multiply say a power matrix 0 1 1 0 to a quantum state vector say 1 0 ket basically ket 0, right? X time ket 0. This is same as this, right? So basically your qubit is here on the block sphere ket 0, right? And you are applying x gate, x Pauli x gate, right? This one. So what it does is basically a 90-degree rotation. It does a 90-degree rotation. Right. So basically it makes your qubit here on gate 1. Right. So this okay, on the blosphere, this opposite polarity means 90-degree rotation. Okay. So so the beauty of, or the good part of the eigenvalue decomposition is that or of the eigenequation is that so when you apply a matrix A to a vector X, so suppose this is your vector X, and it does not change the um, angle of the vector. Suppose this is your X vector, it remains as X vector with some alpha amount, right, or lambda amount, right? So basically, so you applied A on X. So this color is not looking good. So and basically it basically does stretching. So if it is X, and it will be lambda X, right, by applying A. So it only does stretching or scaling, but no change of angle, so that's why basically so by EVD, all the equation Ax equals to lambda X, we say that scalar, this scalar is called eigenvalue. Eigenvalue is such a scalar which does not impact, or does not basically change the direction of the vector which represents some physical phenomena, but it only stretches that vector due to the impact, or due to the activity of the matrix A, right? So that's why when you do basically all the quantum mechanical basically equations, if you look at, right, these energy equations right here, for example, often we see this equation as E psi equals to this H I, right? This is an extremely important equation in quantum mechanics. So these xi are vectors, right? So so E is the energy operator, right? So you find all such lambda in a energy states are basically, you find the energy state as such. It does not basically change the wave function itself, which are the basically eigenstate representation of the wave functions, right? So that's why this equation is extremely important. Now, although there is a formal way to compute eigenvalue decomposition, but just for tricks, like for simplicity, I'll show how to remember this, right? So let's come back to the complexity part. So earlier A has now A is, of course, let's take a n cross n matrix, right? And with and by just doing simply ordinary multiplication or inversion, I have to do order of n to the power 3 complex computations, right? But now if I can diagonalize it in some way, right, then I can save some memory, right? Or I can have some better approach to solve a linear equation, right? Or to solve a ordinary differential equation in quantum mechanics, right? So Ax, right? So let's take so another thing is on quantum mechanics, all the basically state representation of the wave function in the basis set, right? Yesterday we have seen they are orthonormal basis sets, right? And all the eigenvectors are orthonormal vectors. So let's take a1 x1 equals to lambda 1 x1, right? Let me write this equation in a better way such that I do not have to write it again and again. Suppose this is equals to lambda 1 x1, right? So there is a multiplication only, okay? Then I do a multiplication with x2, another vector, another eigenvector, okay? And I am getting another lambda 2, right? So another scalar lambda 2 times x2, for example, right? and so on. I find n number of nth eigenvector, and I find a scalar lambda n, right, and xn. So it can be a diagonal matrix, right? You can see, and this is a matrix with all orthonormal, vectors, right? Basis vectors, orthonormal vectors. So this is called a unitary matrix. If this x1, x2, these are basically real vectors, then they can be Q. If means each xi vector, if they belongs to the real n cross 1, then this matrix will be Q matrix. And if this orthonormal basis vectors are complex, right, n cross 1, this is unitary, and this is orthogonal. Okay, they are same thing, just they are belonging to the complex vector space or the real vector space. Okay, so in general, let's take complex. Okay, and it can be, because a complex number can be, you can always represent as a real plus some 0 times imaginary part, right? So this is your u, right? And this x1, x2, this part you can write it as this u transpose, right? And this is a diagonal matrix because you can multiply x. So basically, a1 x1 equals to lambda 1 x1, a2 x2, lambda 1 lambda 2 x2, an xn equals to lambda n xn. This equation satisfies, right? So this is also, you can write it as lambda u transpose, right? Now you can pre-multiply with u transpose, right? So basically, okay. So left hand side I can write this way: a times this u equals to lambda times u star, right? And okay, so what is the thing is that there is a dimensionality matching I have to do. So basically this is now in general x bar, whether I have taken as a column vector or the this kind of thing, right? So in general, what you can do, so right hand side, so better to write this way. Maybe I have written in opposite way, but that's okay, fine. There is no issue with that. You can always write this way, this lambda, right? So u transpose a u equals to lambda, right? And then a I can write as in u lambda u transpose, right? So this is just how you represent these things. So this is just a shortcut that I have applied, but in general, I should write in this way: a1 x1 equals to lambda 1 x1, and a2 ax2 equals to lambda 2 x2, right? And axn equals to lambda n xn, right? And how you stack them basically. So the way how we stack them is a different way of thing. So basically, you can always write this thing as a u lambda u transpose form, right? So then basically, left hand side, whatever you write, because u star u equals to identity. If you apply this property here, so you can exchange this, how basically you stack them as a x1, x2, and xn as u or u prime. That way you basically represent left hand side and right hand side, and you can always write the second part of the equation as a diagonal matrix time lambda 1 to lambda n times basically another thing, right? So then just swapping. So so this equation is extremely important, and maybe some of the course teacher, or if I get time, so in the next day, or the next week, we'll see something, two primitives. One is called the sampler primitives in Qiskit, and another primitive is there is called the estimator primitive, right? So I'm taking additional 2-3 minutes today. Please allow me. So what it does is that we have seen the eigenequations hx equals to h psi equals to e psi equations, right? This is the equation we know for any molecular thing, or in fact, just this is just an eigen equations, right? And where we are interested is that basically is to find, because this is any general lambda, right? And for if you want to calculate these things, e psi, right? That of course equals to some value, right? Some lambda, right? And I want to minimize this, right? Minimize, suppose this one, right? And that will give me my lambda mean, right? And if it is parameterized with theta, right? I don't know the exact theta, so I can minimize over theta, for which theta it gives the minimum thing, right? And this is called the ground state of a ground state of a molecular Hamiltonian, right? Or a atomic Hamiltonian. Suppose you are interested to compute the ground state or the excited state, conduction band, whatever. So basically, you solve this kind of equations, right? And Qiskit will help you if you can design this observable, and if you know the state encoding of your problem, so you can calculate the lambda mean of your problem. Suppose you have a network, social network or some network, right? And you want to find the suppose and you represent the problem as a graph, and you want to do a clustering problem or graph cut problem, right? So to divide the resources into two part, right, or multiple parts for many regions. So there is max cut or mean cut, right? So mean cut or max cut thing. So basically, there for the network you design a Hamiltonian H, right? And there are lots of hidden variable, right? X, and you formulate the problem very similarly, x bar x star h x, and you try to minimize this, and you don't know, suppose, those hidden variables, right? So the x can be parameterized, or you can directly find for which x this is minimized, right? And that will give you some value, say lambda some star, and from based on that you can calculate the mean cut or max cut problem. So there are lots of problem, and there are algorithms like QAOA and all. So we'll later revisit these kind of quantum algorithms on a later stage in QT-05 or so on. And you will see the application of EBD, SBD, and all these kind of problems. So with this, I conclude the session, and please let me know if you have any question. And there are a lot of things I did not cover, especially the Krylov subspace, Arnoldi. Those are advanced methods. Sometimes we use them in algorithms for various regions. But for now, these are the basics topics I covered. Please feel free to drop questions.
Thank you very much, Mustafizur sir. And if there are any questions, yeah, okay. So
Yeah.
programming on quantum circuit. Yeah, actually, I think,
So,
yeah,
yeah.
go ahead, please.
So this circuit programming thing is not part of QT-03 and 4. So this will be detailed cover in QT-05. Although I gave some basics of some circuit like the swap test circuit. Maybe next week I'll give 2-3 basic circuit like Sadamat thing. So there are other people who will cover this part in detail. So I'm sorry for this. Yeah.
Yeah, actually, I think when we are programming error coding, I think we will have the session by Ritajit Majumdar sir. At that time, he will show some things on Qiskit, right? So we'll do that.
Right.
And Dr. Jay Kumar is also coming up with an assignment questions, which he will try to share in a week's time, maybe
Right.
this week, so that when you have all the participants will have time to try out on Qiskit or Penny or any other tools that he has introduced. So you do all those assignments, and after that you can try to there'll be a session where he'll explain the solutions. So it is not
Right.
only an assignment. The assignment will be discussed, the solutions will be discussed, and he
Yeah.
will take you through because it's all possible to code and show you. So the code will be shown, so you can try to look at that, right? So that's what is the thing. Yeah. So there's one question, I think, how to apply kernel methods to classification problems.
Yeah.
You have given the answer. Yeah.
Sure. So the main objective of kernel is that you have a data set in a particular representation, direct data representation or some feature representation, right? And it is such a if you find that this problem, you cannot directly find a decision boundary to segregate that this is the class A and this is the class B to find a hyperplane, right? So often it is seen that if you can augment this problem to a higher dimension, case one, or if you can convert this problem from domain A to domain B, right? But in domain B, these basically features can be separable by a boundary, by a hyperplane with a affine boundary. So basically, for example, in a one-dimensional case, you have a time series signal and you convert it to the frequency domain, and you can see like in the time domain, you have something like some wave with some basically changes in the wave pattern, but it is difficult to understand in the time domain. When you plot by frequency analysis like Fourier transform, you see there is two peaks. Then you identify, okay, there are two distinct frequency components in the frequency domain. So this e to the power j omega t in the Fourier series, right? That is the kernel. Similarly, on the those who work on the image processing, right? So you have a pixel values, right? So pixel values often difficult to classify things. So you convert the pixel values to some features values. Say, for example, for a mouse, these are certain features. For dogs, these are certain features. Or if you want to classify fruits, so a particular type of fruit and another particular type of fruit, maybe the color is same, but the shape is different. So to go from pixel value color features to the shape feature, you need to do a kernel conversions, right? So for the color to these conversions from color to the shape or this kind of thing, so there is mathematical, this kernel is basically a matrix, right? And you basically have a input features for class 1 and class 2, you do the dot product. Basically there is a function of dot product, okay? And then you convert it to from one domain to another domain and you classify it. This is just an example for that.
Yeah. Regarding the assignment, the initial assignments were practice assignments based on QT-02, whatever was taught. So you should have tried that. Yeah, the solutions will be discussed. I think Jay Kumar sir is going to do it on 27th November. He has given the date. 29th was supposed to be there, but there is some small change. Dr. Anindita will be speaking on 29th. So 27th is where Dr. Jay Kumar will share the solutions. So don't worry, all these questions that are given will be solved. So don't worry about that. And then as sir also mentioned in QT-05, because you already are aware of all the programming thought process, we'll run the algorithms and give you the solutions at that time in QT-05, right? So don't worry about that. Thank you so much. So thank you, sir. Thank you for your valuable time, and 3-hour lecture is a challenge. After 3 hours also, you have the same passion to answer the queries. So thank you, participants. I think it was a lightly loaded session today, but yeah, because that's very important to cover the mathematics. That's why we have asked sir to take it, and then he's covering next week also. Please remember, Saturday, 3 hours. Right. Today also, many of you were unhappy that 2 o'clock we did not remind you in earlier. We will do that next time. We will remind you in the morning on Sunday. But yeah, those who have missed the initial part, you can go back and look at the video. The lectures are already shared, so you can take that. So please note it. Next Saturday also it will be 3 hours. Next Friday will be 2 hours. And please also note tomorrow is off. So don't call me at 3 o'clock, sir. The session has not started, right? So you're all so much used to the 3 o'clock time. I understand that all of you. I get calls. Please understand. On holidays and Sundays, I get a call.
I think
Sir, session
beginning
has
this
not
year,
started.
yes, sir. So beginning this year until now, I think it's November, almost 10 months, 11 months. Sir
Yeah,
is
yeah. So
continuously every day you are putting effort for many courses, right? So yeah.
Right. Yeah. We
They will.
simultaneously ran courses also. And of course, my colleagues, these initial 3-4 courses I am there. And after that, we have other sessions also. Yeah. And yeah, appreciation for Mustafizur sir is always there. So thank you so much for the time. And hope you all enjoyed. So please go back, refer, review. Notes will be shared. Whatever examples, as far as handwritten notes is already shared. So please look at that. Today's notes will be shared. So please go through and prepare well. And next week, I think there'll be one small change we'll try to do because sir is closing on 22nd. We will open the quiz on 23rd. Right? We will include sir's lecture also. The content of 22nd also into the content. So please, small change. We'll give you more time to prepare. No problem. We'll keep it open till the end of the course, and then you can complete the quiz 3. So please note that quiz 1 will be closed on Monday evening, and no more extensions will be given after that. Quiz 2 will be open at the same time, so you can conclude, right? So thank you so much, Mustafizur sir. We will meet on Monday morning. Monday morning, we will have lectures by Dr. Ritajit Majumdar. He will be sharing on various sessions on quantum errors and mitigation. So I will remind Dr. Mustafizur also. Thank you so much. All the participants, thank you so much for being till the end. Thank you.
Thank you.